Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
Hello, and welcome back to another exploration. I am genuinely thrilled you are here today because we are tackling a subject that sits right at the intersection of our wildest science fiction dreams and, well, the hardest, coldest realities of physics.
It really does.
We're looking at a stack of research today that, I'll be honest, it feels a bit like a roller coaster.
That's a perfect description.
It takes you up to this highest peak of excitement, and then it just drops you into a free fall of disappointment. But then, and this is the weird part, it loops you around into something completely unexpected and, frankly, much more profound.
It really is a journey of good news, bad news, and then weird news. We're dealing with a topic that everyone thinks they understand because of, Hollywood.
Oh, absolutely.
But the actual physics behind it has just undergone a massive shakeup. We're looking at a paper published just recently in January 2026 by Enrique Gastañaga and his colleagues, and it forces us to rethink the structure of the universe itself.
We were talking about wormholes.
Wormholes.
The cosmic shortcut. The Einstein-Rosen bridge. You know the image? You fold a piece of paper in half, punch a pencil through it, and suddenly you can jump from Earth to the Andromeda Galaxy in time for lunch.
Right.
It's the backbone of interstellar contact, Star Trek. I mean, basically, if you need to move a plot faster than the speed of light, you use a wormhole.
Exactly. It's the ultimate narrative device. It solves the biggest problem in space travel, which is that space is just, annoyingly impossibly big.
Yes.
We want a subway system for the stars.
We do. But, and here comes the record scratch moment, this new research suggests that this subway system is permanently closed.
Or maybe that it was never a subway system to begin with.
Right.
That's the hard truth we have to lead with. According to this new analysis in the journal Classical and Quantum Gravity, the traversable wormhole, the kind Matthew McConaughey flies a spaceship through it likely does not exist. It can't exist.
I have to say, when I first read the headline, I felt a genuine pang of loss.
I get that.
There's something so hopeful about the idea of a wormhole. It makes the universe feel accessible. Losing that, it feels like we're being trapped in our own backyard.
I completely get that. It is a disappointment if you look at the universe as a place to, conquer or travel through. But I want to pivot your perspective a bit, because what Gastañaga is proposing is that while we lose the shortcut, we gain an answer to a much, much bigger question.
Which is?
The origin of everything.
Oh.
This research suggests that these structures aren't tunnels for spaceships. They are mirrors for time. And these mirrors might be the reason we're here at all. They might prove that our Big Bang wasn't the beginning, but a bounce.
Okay, mirrors for time and bouncing universes. That is a lot to unpack. So our mission today is to figure out how we got from sci-fi tunnel to this new theory.
Right.
We need to understand why the old wormhole idea failed, what this mirror actually is, and why it implies we might be living inside a black hole right now.
And we're going to see how this attempts to solve the biggest headache in physics, the absolute war between gravity and quantum mechanics.
So let's rewind. Let's go back to the source. Most people hear Einstein-Rosen bridge, and they assume Einstein sat down in 1935 trying to figure out how to travel faster than light.
Which is completely wrong. We have to contextualize where Einstein was in 1935. He wasn't thinking about spaceships.
Right.
He was thinking about particles. Specifically, he was frustrated.
Frustrated with what?
With singularities. In his theory of general relativity, if you crunch matter down enough, you get a point of infinite density, a singularity.
And that's where the math breaks.
The math breaks. It turns into nonsense. Einstein hated that. He felt that nature shouldn't have divide by zero errors.
So a black hole is essentially a divide by zero error in the universe.
In the math of relativity, yes, at the very center. At the same time, you had this emerging field of quantum mechanics dealing with electrons and protons, treating them as point particles, infinite density dots. And Einstein and his colleague Nathan Rosen wanted to get rid of these points. They wanted a geometry that was smooth everywhere, no sharp edges, no infinities.
So they weren't building a tunnel. They were trying to build a better electron.
Exactly. That is the part history often forgets. They propose a model where a particle isn't a solid dot, but a tiny bridge connecting two sheets of space-time.
2 sheets.
Yeah, imagine 2 parallel pieces of paper. The particle, in their model, was a little tube connecting a point on the top sheet to a point on the bottom sheet. To them, the Einstein-Rosen bridge was a model for an elementary particle.
So it was a way to have mass and charge without having a singularity at the center.
Precisely. It smeared out the pointiness of the particle into a smooth geometric structure.
That is wild. So the original wormhole was microscopic.
It was intended to be, yes. It was a mathematical hack, a really clever one, to save physics from infinities. The idea that you could scale it up and, drive a car through it, that didn't come until decades later.
So how did we get from math hack for an electron to let's fly a ship through it?
That shift happens much later, in the late 1980s. Physicists like Kip Thorne,
The guy who consulted on Interstellar.
the very same, he and others started asking the what-if questions. They took the Einstein-Rosen math and said, okay, forget particles. What if this structure was macroscopic? What if it was huge? Could we send a signal through it? Could we send a person?
And that is when the sci-fi dream was born.
Right. But almost immediately, the math started screaming, no. And this brings us to what we can call the pinching problem. This is the part that kills the sci-fi dream, so we really need to understand it.
Okay, lay it on me. Why can't I fly my spaceship through the bridge?
Because the bridge is dynamic. It's not a static hallway. It's not like the Lincoln Tunnel.
It's not just a hole in space.
No, it's a structure made of space-time. And space-time is governed by gravity. And gravity, is an attractive force. It wants to pull things together.
So it wants to close.
It wants to collapse. And inside this bridge, the gravitational forces are immense. The math shows that it collapses basically instantaneously.
Define instantaneously. Like, I open the door and it shuts in 1 second.
Faster. Much, much faster. It shuts faster than the speed of light.
Wait, hold on. I thought nothing moves faster than light. You can't just say faster than light and get away with it. That's like rule number 1.
Good catch. And you're right. Nothing travels through space faster than light. But space itself. Space can do whatever it wants.
Ah, the loophole.
The loophole. Space can expand or contract at any speed. It's the fabric, not the things on the fabric. So imagine you open this wormhole. You're standing at the entrance. You see the light from the other side. Let's say the Andromeda galaxy.
Okay, I see the pretty spiral galaxy on the other side.
You take one step forward. But the tunnel, the space-time of the bridge itself, is collapsing so fast that the ceiling and floor meet in the middle and pinch off.
Okay.
And this happens before the light that was at the threshold can even reach the middle of the tunnel.
So, you can't even get halfway through before it's gone.
You can't even get started. You literally get crushed into a singularity before you can cross. The bridge disconnects itself from the universe before it can be traversed.
So it's a trap. It's not a bridge.
Yeah.
It's a cosmic mousetrap.
In its natural state, yes. It's designed to fail. Unless you prop it open.
And this is where the sci-fi writers say, activate the shields, or use the dark matter, or some other technobabble.
They usually say exotic matter. And this is a real term in physics, but it is often misused. To keep that throat open against the crushing weight of gravity, you need something that pushes back. You need anti-gravity.
Anti-gravity, I mean, that sounds pretty exotic to me.
Effectively, yeah. You need matter that has negative energy density.
I am going to stop you there. Negative energy. That sounds like a mood, not a physics term. I know what energy is. It's heat, it's light, it's motion. How can you have less than zero energy?
It is a brain bender. I mean, it's one of the weirder concepts out there. Think of empty space as having a baseline energy, the vacuum energy. We usually just call that level 0.
Okay, the floor.
Right. Positive energy is anything above that floor. A planet, a star, a battery, you. Negative energy would be a region where the energy is lower than the vacuum state. It's a dip in the floor.
Is that even possible? Or is this just a number on a spreadsheet that makes an equation work?
Well, we have seen hints of it. We've created tiny, tiny amounts of it in labs using something called the Casimir effect. Basically, you squeeze 2 metal plates so close together that you squeeze out some of the vacuum fluctuations between them.
So you create a little patch of less than nothing.
A little patch of less than nothing that creates a tiny attractive force. But to hold a wormhole open, a human-sized one, you would need Jupiter-sized amounts of this stuff.
And we don't have a Jupiter-sized bucket of negative energy lying around.
We haven't found a single ounce of it in nature on that scale. It is purely conjectural. It's a theoretical requirement, but there's no evidence it exists in the quantities needed.
So the final verdict is no scaffolding.
No scaffolding.
Mm-hmm.
Without the negative energy, the bridge snaps shut instantly. The subway is closed permanently.
Okay, so the door is slammed shut. The subway is out of order. And usually, this is where we would pack up and go home, story's over. But Gastanga and his team looked at this broken bridge and said, wait, we're looking at this all wrong.
This is the pivot. This is the brilliant part. They said, if general relativity forbids travel, maybe the bridge isn't for travel. Maybe it's serving a different function in the universe. It's not a bug, it's a feature.
And this brings us to the mirror concept.
Yes. They stopped looking at the bridge as a connection between place A and place B. They started looking at it as a connection between universe A and, well, a reflection.
The reflection in time.
Correct. And to get this, we have to talk about symmetry. Physics, at its absolute core, is just obsessed with symmetry.
Obsessed how? What do you mean?
Well, look at the fundamental laws. Newton's laws, Einstein's relativity, even Schrödinger's equation in quantum mechanics. If you look at the raw equations, none of them have a preferred direction for time.
What do you mean? Time definitely has a direction. I am older than I was 10 minutes ago. My coffee got cold. It didn't spontaneously get hot again.
That is your macroscopic experience talking. And you were right. In our big, messy world, time has an arrow. We call that entropy.
Right. The universe gets more disordered over time.
Exactly. Things get messier. You break an egg, it scrambles. It never unscrambles itself and goes back into the shell. That's the arrow of time we experience.
Right.
But zoom in, way in. Look at a single atom bumping into another atom, a single billiard ball collision. If I recorded that on video and played it backward, would you know?
No, I guess not. It would just look like another bounce. The physics would look the same.
Exactly. At the microscopic level, the fundamental laws of physics are time-symmetric. They work equally well forward and backward. There is no arrow of time in the fundamental equations themselves. The arrow only emerges when you have billions and billions of particles interacting.
Okay, I accept that for atoms. But how does that apply to the wormhole, this giant structure?
Guston Yaga's team argues that the Einstein-Rosen bridge is the place where this fundamental symmetry becomes physically relevant on a large scale. It's a structure that connects two regions where time flows in opposite directions.
Okay, hold on. Time flows backward. I hear those words, but my brain rejects them.
Mm-hmm.
What does that actually mean? Are people walking backward? Is the rain falling up into the clouds?
It's not about movies playing in reverse. That's a common misconception. It's more fundamental. Think of it as a balance sheet for the universe. To make the math work, to keep the energies balanced and the quantum symmetries intact, you need a counterbalance.
A yin and a yang.
A yin and a yang. The wormhole isn't a tunnel to a new location. It is the hinge point. It's the joint. On one side of the hinge, you have our universe, where entropy increases and what we call time moves forward.
Okay. Our side.
On the other side of the hinge, mathematically, there has to be a complementary state. A state where, from our perspective, entropy is decreasing, where time flows in the reverse direction relative to us.
So is a mirror universe?
In a temporal sense, yes. It is the necessary other half of the equation. It's not a place you can visit. It's the other side of the coin that makes the coin exist.
And we don't see it because we're stuck on our side of the coin.
Exactly. We only see the forward half because we live in a big, high-entropy world. But near a black hole, near that extreme gravity where the bridge exists, the structure becomes relevant. The bridge is what stitches the two arrows of time together into one complete system.
So the wormhole is the seam.
Yes. It is the seam between the forward time reality and the backward time reality. Without both, the physics is incomplete.
That is deeply abstract. But I want to ground this because the research says this actually solves a massive practical problem in physics. The black hole information paradox.
Oh, this is the big one. This is the 40-year-long war in theoretical physics. This is the issue that kept Stephen Hawking up at night.
Set the scene for us. Why is this a paradox? What's the problem?
Okay. So in the 1970s, Stephen Hawking did this incredible calculation. He combined quantum mechanics and general relativity near a black hole's edge, and he realized that black holes aren't perfectly black. They radiate.
Hawking radiation.
Hawking radiation. They glow with a faint heat, and because they're radiating energy, they're losing mass. Over trillions upon trillions of years, they lose all their mass, and eventually they evaporate. They disappear completely in a final poof of radiation.
Okay, so the trash can of the universe eventually empties itself. Why is that a problem?
Because of what was inside the trash can.
Yeah.
Let's say I write a diary, all my deepest secrets, the complete information about my life, and I throw it into a black hole.
Very secure disposal.
The most secure. But according to a fundamental rule of quantum mechanics, information is never lost. The universe is unitary.
Unitary.
It means that if you had a supercomputer and you could track every single photon and particle in the universe, you should, in principle, be able to rewind the clock, and reconstruct my diary from the ashes.
Like putting a shredded document back together if you have all the pieces?
Exactly. The information is scrambled, but it's not gone. But Hawking's math showed that when the black hole evaporates, the radiation that comes out is random. It's thermal gibberish. It contains no information about my diary. The information is gone, erased, deleted from the universe.
And quantum mechanics says, you can't do that.
Quantum mechanics screams, illegal move.
Yeah.
But relativity says, sorry, the black hole is gone. This is the paradox. One of our two best theories of reality, has to be wrong.
And physicists have been trying to fix this for decades.
With all sorts of complicated, bizarre ideas.
Yeah.
But here's how the time mirror fixes this. It's just so elegant. It redefines the event horizon. We usually think of the event horizon as the point of no return, a cliff edge. You fall off, you get crushed, your information is lost in the hole forever.
Right.
But if the bridge at the center is a time mirror, the event horizon isn't a cliff. It is the entryway to the bridge. The information in your diary crosses the horizon. But instead of being destroyed in a singularity, it passes through to the mirror side where time runs backward.
Wait, so the information doesn't vanish. It just exits stage left into the past.
It continues to exist and evolve, but in the reverse time frame. It flows into the other side of the symmetry. This means the information is conserved. It's still in the total universe, the bi-universe system, you could say.
So quantum mechanics is happy.
Quantum mechanics is happy, but it has left our observable region of forward-flowing time, so general relativity is also happy. The paradox just dissolves.
That is incredibly elegant. Feels like a magic trick. Is the rabbit in the hat? No, it's in the other hat. You just needed to know there was a second hat.
That is often how physics advances. You realize you were only looking at half the system. The solution was there all along, hidden in the symmetry of the equations.
Okay, so we fixed black holes. That's a Nobel Prize right there. But the source material goes way bigger. It takes this mirror idea and applies it to the whole enchilada, the Big Bang.
This is where we move from interesting physics to existential crisis.
Am I ready? Bring on the crisis.
If the universe loves symmetry, and if black holes act as these time bridges, then what does that say about the moment everything began, the ultimate singularity?
The standard story is 14 billion years ago, there was a point of infinite density, the Big Bang. Time starts at zero. Everything explodes out of that singularity.
Right. Another singularity, another divide by zero error that physicists have never been comfortable with. But this theory suggests, what if the Big wasn't the beginning? What if it was a bounce? Imagine a universe before ours, a parent universe. Maybe it expands for a while, but eventually gravity wins. That universe stops expanding and starts collapsing. It crunches down. All the matter, all the stars, everything squeezes into a tiny, hot, dense point.
The big crunch. And normally, that is where we think it all ends, a final singularity.
But if this bridge mechanism is real, it doesn't end. It doesn't hit an infinity. It hits that maximum density, crosses the symmetry point, the mirror, and reverses. That collapse turns into an expansion. Time reflects. The implosion becomes an explosion.
And that explosion is our Big Bang.
Precisely. We are the exhale of a previous universe's inhale.
That is a beautiful image. It makes the universe feel like a lung, breathing in, breathing out, potentially forever.
It removes the need for a creation moment out of nothing, which has always been a philosophical sticking point. It implies an eternal chain of universes, each one giving birth to the next.
But there is a specific detail in the report that made my hair stand up. It says, and I'm quoting, "Our universe might be the interior of a black hole formed in another parent cosmos."
Yes, this is the nesting doll theory of the cosmos.
Explain that. How can we be inside a black hole? I look up at the night sky and I see stars. I don't see a ceiling.
Think about the geometry from both sides. From the outside, in the parent universe, a giant star collapses. It forms a black hole. It creates an event horizon. Matter falls in.
Okay.
But what does that matter see from the inside? As it crosses the bridge, the math says it experiences a moment of infinite density that immediately blossoms into a rapidly expanding space.
That sounds exactly like our expanding universe, viewed from the inside.
It is mathematically identical. The interior of a black hole in one universe can be the Big Bang of a new universe, the event horizon of that parent black hole. From our perspective, that's the boundary of our observable universe, the cosmic horizon beyond which we can't see.
So we are living in a bubble blown by a collapsing star in a bigger reality that we can never access.
That is the staggering implication, yes.
Which begs the question, if we came from a parent universe, did anything survive the trip? Is there any luggage from the old world?
That is the billion-dollar question. If the bounce is messy, if it's not a perfect, clean reset, then some things might get through. Some structures might be robust enough to survive.
Like what, for instance?
Well, source material speculates about primordial black holes. These wouldn't be black holes formed from stars in our universe. These would be small, super dense black holes formed in the parent universe that managed to survive the transition.
They rode the bounce.
They rode the bounce. And here is where it connects to another one of the biggest mysteries in all of science.
Dark matter.
Dark matter. We have this stuff. We know it's there because of its gravity. It makes up 85% of the matter in the universe. We can't see it. We don't know what it is.
We have been hunting for a new kind of dark matter particle for 40 years, and we've found zilch. Nothing.
Exactly. The experiments keep coming up empty. So some physicists are starting to ask, what if we're looking for the wrong thing? What if dark matter isn't a new particle at all? What if it's just a swarm of these ancient primordial black holes?
Whoa. So the dark matter holding our galaxy together right now, it might be the ghosts of the previous universe.
It fits the profile perfectly. They would be invisible because they're black holes. They would have gravity, a lot of it, and they would be everywhere, scattered by the Big Bang. It is a stunning thought that the gravity keeping you in your chair might be generated in part by relics from before the Big Bang even happened.
That is, I don't even have a word for that, but I have to play the skeptic here. This sounds amazing. It sounds poetic. Mirrors, balances, ghosts from another universe. But is it just math on a whiteboard? Is there any actual proof? Can we test this?
I am so glad you asked that, because a theory without evidence is just fantasy. And this paper, this is the kicker, it claims to have a smoking gun.
And it's in the cosmic microwave background.
The cosmic microwave background, the CMB, this is the afterglow of the Big Bang. It's the oldest light in the universe, a baby picture of the cosmos when it was just 380,000 years old.
And usually, we are told it is incredibly uniform. It is the same temperature everywhere with tiny, tiny fluctuations.
Roughly, yes. To the naked eye, a map of the CMB looks like TV static, random noise. But for about 20 years now, cosmologists have been staring at this static and noticing something weird, something that shouldn't be there.
An anomaly.
A very specific one. We call it the parity asymmetry.
Break that down. What is parity asymmetry?
Okay, imagine you're looking at that map of TV static, the CMB. You expect it to be totally random. But if you look closely at the patterns of hot and cold spots, you realize the patterns on the left side of the sky are slightly different than the patterns on the right.
It's lopsided.
It's lopsided. It's as if the universe has a preferred direction. One of its mirror images is slightly different from the other.
And the standard Big Bang theory says that shouldn't happen.
The standard model of cosmology is built on the idea that the universe is isotropic, the same in all directions. It says this lopsidedness has to be a fluke. A statistical 1 in a million accident, like flipping a coin 1,000 times and getting 600 heads. It's possible, but it's really, really suspicious.
And it's just a fluke is never a satisfying answer in science.
Exactly. Physicists hate relying on luck. But here is the massive victory for the mirror theory. If you plug in the math of the time mirror, if you include the influence of that backward time universe on our own during the Big Bang, the lopsidedness isn't a fluke. It is a prediction.
Wait, really? The theory actually predicts the static should be lopsided.
Yes. The interaction between our universe and the mirror state during the bounce naturally creates exactly this kind of asymmetry. It breaks the perfect mirror symmetry in a very specific, predictable way.
So that weird blemish on the baby picture of the universe, that isn't a mistake in the photo. That's a fingerprint.
It is the fingerprint of the reflection. It is evidence that the other half of the system, the mirror universe, exists and had an influence on us. It takes a bug in the old theory and turns it into a core feature of the new one.
That gives me goosebumps. Because it anchors all this wild speculation, living in black holes, time flowing backward. It anchors it to something we can actually point a telescope at and measure.
That is what makes this paper so exciting. It is not just philosophy. It's testable physics. And the first test seems to be a pass.
So let's wrap this up. We started this investigation feeling kind of bad about the death of the wormhole. We lost our warp drive. We are stuck taking the slow boat to Alpha Centauri.
We are, and I don't want to minimize that. For space travel enthusiasts, it is a blow, no question.
But look at what we gained in exchange. It's an incredible trade.
We traded a transportation tunnel for a mirror into the fundamental nature of time. We traded a simple shortcut for an eternal cycle of birth and rebirth.
We gained a view of a universe that doesn't just start and end, but bounces. A universe where time is a two-way street at the deepest level, even if we can only walk down one side of the road.
And it connects everything. It suggests the laws governing a single particle are the same ones that govern the entire cosmos. It suggests that Einstein's relativity and quantum mechanics aren't enemies. They are two sides of that mirror.
I have one final thought I want to throw at you. A provocative thought to send our listeners home with.
Let's hear it.
If we are possibly living inside the interior of a black hole from a parent universe, and our universe is full of black holes.
I see where you're going with this.
Does that mean every black hole in our sky contains a baby universe inside it?
That is the logical conclusion of the theory, yes.
Are we living in a nesting doll of realities? Is universe is all the way down?
It is entirely possible. Every time a massive star collapses in our galaxy, it might be the Big Bang for a new reality that we'll never know we exist. And we, in turn, might just be the offspring of a single collapsing object in a universe we can never see.
That makes the night sky look a lot different. Those aren't just dark spots up there. They might be seeds.
They might be seeds. I like that. A cosmic garden.
Well, on that mind-bending note, we are going to close this investigation. Thank you for going on this journey with us through the wormhole, into the mirror, and out the other side.
It was a pleasure, a real trip.
Go outside tonight. Look up. Think about the bounce. We will catch you next time.